Hello, Python programmers. Let's talk about manipulating data in a data frame. My plan is to discuss the not a number concept and value in general terms, show some simple examples, and then we'll cobble up a small data frame of a couple of rows on our own just to have some data to work with. Then we'll add some data and remove some data to illustrate how that can be accomplished. Then we will look at what happens when there's missing data, particularly focused on NaN. And then finally we'll generate a plot from our data. As always, well, not as always, but when we're using pandas and NumPy, we'll add the include statements. There I go again, using the wrong term. Include is a different programming language. We'll use the import statements to bring in the pandas library and the NumPy library, aliasing them appropriately. Pandas is typically aliased as PD and NumPy is typically aliased as NP. And I included in our notebook file one cell dedicated to just NaN concepts. Remember, NaN stands for not a number. We have a need when representing floating point values to somehow create a flag or a semaphore telling us that what is stored in this variable isn't really a legitimate number. It's a floating point type, but you can't do anything with it except compare. That means that a calculation has gone wrong. We divided by 0 or did something out of the ordinary, took the thing out of range, or it just hasn't been provided, which is the case in a data frame perhaps where you've read some data from a CSV file or scraped a website. Sometimes not all of the data in all of the rows has been made available to you. We live in the real world. Data goes missing. So we have this thing called NaN. It's part of the NumPy library. But remember, NumPy is the basis for pandas, so a lot of the pandas data structures have their roots in NumPy. Therefore, you see the NP appearing there. The first thing I'd like to point out is we can't use the traditional comparison operator, the test for equality, when we're looking for NaN. We can't use equal equal. The test for equality in Python when using strings and ints and booleans and floats is equal equal, but the test for equality when checking for NaN is math.isNaN. So we're using another library called math here, and at the very bottom of this slide highlighted in yellow, I'm demonstrating the correct way to check for the presence of NaN when you have just a standalone scalar value. If you don't have a standalone scalar value like alpha, if it's not just its own simple little variable without a home, if it's part of a data frame or part of a NumPy array, we have other functions we can use to detect not a number values. Now I'm going to take this just a little bit farther. I will show you that in the notebook file there is the cell. First I'm going to run the import cell so I don't have to do that ever again. And in the second cell is all of that NaN logic that you can take a peek at. The first if else just simply demonstrates that we can't do an equal. We can't do a test for equality between two values that are known to contain NaN. Even though they both contain the same thing, we can't do it. Also notice that there are a couple built-in representations of not a number. One is uppercase n's and one is lowercase n's. As far as I know, those are the same thing. I threw it in there because it appears to me to be some kind of anomaly. I'm not that much of an expert on the structure of the NumPy library. My guess is that it's a historic thing, that at some point maybe two libraries converged into NumPy and they maintained both of those NaN semaphores. Or maybe one person started writing the library and they used one version of that, NaN, and another person used lowercase. And in order to make all the code compatible, they maintain both of those. Now, I could be completely wrong about that. That's just my speculation. Those two if-else expressions then demonstrate what you cannot do. We can't do that. I'll add a comment to this. We cannot use equal, the test for equality operator, to check for NaN. And that matters because sometimes we don't have data and we need to know that we don't have data. At the bottom of the slide there is the correct way to do it. math.isNaN, and then you pass that function the variable that you're interested in. In this case, I did a math.isNaN function call on the variable alpha, and it does print out the correct result. Alpha is NaN. Let's do a little bit more with this. I have a completely blank notebook. I'm going to bring in the math library, and then I'll just, to give me something to work with, I'll say epsilon equals, and I want to set it to NaN. And if I look back at the notebook that I gave you, I'm going to use np dot NaN. np.nan, and that works. At least, oh, it doesn't work. I didn't bring in NumPy. My bad. I just told you to do that. NumPy as np, so fix that. Now it should work. There it goes. That was scary. Now I have a variable epsilon that is not a number. It's a floating point type. I can print the type of it. And I can see that it is designed internally to store decimal places and numeric values, but it's not. If I print the variable itself, it does print out NaN. And interestingly enough, Python prints it out in all lowercase, even though I use that uppercase initializer, np.capital N, A capital N. Well, what can I do with this? I can detect it. I mean, that's simple enough. We detected it in the notebook that I gave you by using math.isNaN. We know how that works. But can I do anything else with it? Let's just try. Can I add to it? Can I add 1 to not a number? And I will print it again. It remains NaN. You can't recover from NaN. Once you get there, you can't get out. Can I create an NaN mathematically? Beta equals 100.5 divided by 0. Dividing by 0 creates infinity. If you're taking a pure math class, you know that there's a symbol for infinity. It's that number 8 kind of turned on its side. Looks like a racetrack. But if I divide by 0 inside a computer, there's no such thing as infinity. But what does beta become? Well, the couple things could happen. It could crash and give me an error, a big pink window with a nasty error message in it. Or it could maybe store some unique flag, some unique indicator value in that variable telling me that something went wrong. And let's be optimistic and let's hope that it doesn't crash. We'll put a print statement in there, and it does. So that's not a way to get to NaN. Could I go out of range? Is it possible to increment a floating point number enough times to where it exceeds its capability and I simply can't store any more information in it? It just gets too big. I wonder if we could do that. Let's cobble up a loop for I in range, oh, I don't know, 0, comma, some really big number. And then let's say beta equals beta times 10 plus 1. We'll just do some simple mathematical operation. Before we do that, let's set beta equal to 0. Now, we're doing things that are dangerously close to computer science or IT. The point here, though, your takeaway is that there are things that can happen to a floating point number that are handled differently than all other kinds of numbers. I mean, the concept of an NaN is unique, and I just want you to be exposed to it. In this example, then, I plan to multiply this number by 10 and add 1 a whole bunch of times. I don't know how many. I just typed in a boatload of zeros. It looks like about 100 million times. And that probably won't overflow it, but let's see what happens. After this loop finishes, and I know a lot of you are probably yelling at your screen right now because I'm asking this thing to loop 100 million times. That could take a while in Python, but we'll see. After that loop finishes, crossing our fingers that it will finish, we'll just print beta. Look down in the lower left. It says busy. My program is running. And I'm a little bit concerned now as a developer, just playing the part of a neophyte here. I don't know if it's locked up. I don't know if it's ever going to finish. Maybe I did something wrong. In reality, it's counting up to 100 million. In a compiled language, in C#, this is trivial, but in Python, we're asking it to do quite a bit. I'm going to let this run. I'm not optimistic that it will finish before I retire. I'm exaggerating. But I can go back to the other tab. Theoretically, notice now that the indicator at the lower left goes to idle. So theoretically, I can continue my work in this other tab and periodically check back to see how I'm doing over here, and we might get some kind of interesting result before the end of this video, or we might not. I'm going to slide forward then, and we've talked enough about NaN to get your interest up, I hope. Remember, don't use equal equal. That's really the bottom line. You can't compare two things. You can't compare a float to NaN using equal equal. All right, we need a little bit of data, as I promised. I'm going to create a series, and this series has nothing in it but a column. If I look back at the slide again, I'll catch us up. Here's my slide. This is slide 5, and I'm creating my series, and I'm building in an NaN on purpose. Now the data comes from Google. Google knows everything about everything. If you type in the name of a stadium, it gives you some statistics about that stadium, and I just adapted that to be my data. And I said for the sake of argument that I wanted the name of the team, the stadium they played in, the capacity of that stadium, and then the opening date of that stadium. But I'm saying that I don't know the capacity. For whatever reason, I couldn't find it. I lost it. I was scared to put it in. I don't know. But I decided I would replace that with NaN. And in the notebook, after I create that series from that list, a series from a list, I get a column. I get the default index over on the left, 0, 1, 2, 3, 4. I get the data type of object, which means that one or more elements in that column are strings. They can't be represented as some other more specific type. The object type is the most general type. And then I get the NaN as I expected. Also notice one little curiosity that when I print the series, the NaN is capital N, lowercase a, capital N. But when I printed the NaN up above in the previous cell, I'm sorry, go back to the other work notebook I was in. When I printed NaN in that other notebook, it printed lowercase n, lowercase a, lowercase n. They're the same thing, and Python does not even use them consistently. Sometimes if it's a scalar value like epsilon is here, it prints all lowercase NaN. If it's a member of a series, as it is in the notebook I gave you, it prints capital N's. But they're both the same thing. I have a series. It renders as a column when it prints. It has no index. It has no column heading. And then the next thing I do on slide 6, arbitrarily I decide I don't know what the city is. And I take the city out and I replace it with none. Now what is none? None is similar to NaN, except it applies to a string value. And you can see it renders in blue, so it's a keyword or a function. I think in this case it's a keyword. So that's the way of saying that there's no data in that string field. I have two ways then of communicating missing data. For objects or strings, I can say none, capital N-O-N-E. And for floating point values, decimal values, I can say NaN. Back in my notebook again, just take a peek, and my loop is still running. My attempt to destroy this variable is still progressing, but I don't know where I am. I may only be a third of the way through that 100 million loop iteration, or I may be almost done. There's just no way to tell. My poor little laptop is just working as hard as it can. Now I print this thing out and I have none where the city used to be. I have NaN where the capacity should be. On the next slide, here's where me as a data scientist gets concerned. That's bad grammar. Here's where I as a data scientist that's not right either. I don't know. Here's where we as data scientists get concerned that we need to know if data is missing. So we call a function called not null on the series. That tells us whether or not there is anything in that row. And when I print out series dot not null, it tells me that the row where the city would be is false and the row where the capacity would be is false, meaning it caught the NaN and it caught the none. Both of those fall into the category, as far as Python is concerned, of a null value. For those of you that have studied SQL Server and written queries, there's a null keyword in Microsoft SQL that lets you check and see if a value has been provided in a row of a table. So if you've got a field in your table that represents the capacity of a stadium and that data was never provided, it would have the keyword null in it. But this null is a catch-all, and it's grabbing or detecting both strings and floating point missing values. And that's very useful to us because once we have this new series, it looks just like a series, doesn't it? Once we have this new series of trues and falses, we can use that as a flag, also referred to as Boolean addressing, to print out only the values in our data series that have data. So we can skip over the things that are missing. And on the next slide, we do that. We use mySeries.notNull as an index into mySeries. Note the square brackets there. This is not list syntax. This is indexing syntax. And pandas interprets this as use the contents of mySeries.notNull as flags whether or not to print the individual rows in the mySeries series. One line of code allows us to extract all the non-missing information. Now if I go back to Jupyter Lab again, I can tweak this very easily. Watch, if I just put a not in front of that, so my Boolean addressing now becomes not mySeries, not null. I'm saying give me the ones that are null. Give me the rows in this series that are missing. And that doesn't work because I don't think I ran all the cells. Forgive me, let's go back here. I need to run these cells to catch up. Okay, now I ran the cell I just created, that series. At least I think I did. There it goes. And I don't need to print these. That's not doing it. I need to remove the city, so I need to run that cell. I don't need to run this cell. It doesn't change any data. And now I can do this, I hope. It still doesn't work. And since that didn't work, I am not going to take us down that road right now. So I will just remove that not and rerun that cell. I'll look at that later. The next thing I'm going to do is make a little more data. And we're going to create a data frame now from a list of lists. And each one of these elements in this list of lists could be a series. And we could go through the series step and then do a concat to make each of those series, all of them, into a data frame. But instead of doing the series step, we'll simply pass each of those lists to the data frame constructor, bypassing that step of making individual series, because there's no index and there's nothing that they need to have in common right now. Once I call that constructor, passing it that list of lists, I get a data frame with 3 rows in it. Now this data frame doesn't have any empty data yet, which is fine. I've provided everything. It does look a little bit different when you print this data frame because each of these lists becomes a row. And then each of those rows has columns, and each of those columns has its own data type. And when I print the info on that data frame, I call the info function on the data frame. It tells me what the data type is of each of those columns. And that's determined by examining all the data in that column, all the data in every row. And the only row that is not a string is the capacity column, and it's an int 64, which means for your purposes, just to be silly, it's a really big integer. The pandas library saw no decimal points, and everything it saw, 65,535, 67,895, and 71,008, everything it saw there could be converted to an integer value, and therefore it chose int 64. Now, if you're a total computer nerd, then 65,535, 65,535 is a number of great significance to computer nerds. And if you're watching this video, email me and tell me what the significance of that number is, and I will give you some extra credit points. Back to the slides, we have created our data frame. In slide 9, we have taken out, in slide 10, the capacities. So we got a little bit confused and we decided the capacities shouldn't be in there anymore. We still want the column. So I'm not removing the column on the data frame. I'm just replacing the data with NaN. Simply as an exercise to show that it is possible to do this. And the beautiful part here is the slicing that's taking place. I'm using iloc, which is indexed locations, and in the brackets are the indexes into the data frame of what I want to refer to. So I'm saying I want rows 0 through 4, and remember the 4 is exclusive, so it's actually 0, 1, 2, and 3. And then I want column 3. That's 0 based, so that's actually physically column 4. What happens then, whoops, is that everything under that index gets replaced with NaN, and that ends up being just everything in the third column. If you have a reason then to replace an entire column with a single value, or you could replace it with an entire series too using this strategy. It's easy to do with iloc. Back into the notebook, I am doing that right here. And I should definitely run this cell because and I am having a tough time because I guess I didn't run something else. I didn't create the data frame. There, now I created the data frame, and now I can run the logic to take out the capacities. So I have 3 rows in my data frame now. I have the team name, the city, the stadium name, but I don't have the capacities anymore. All I have are NaNs for those. The next thing I want to do is I don't want that column anymore. If there's any missing data in my data frame, I don't want it. It's getting in the way. It's messing up reports. I only want rows with complete data. So I can call drop NA, and this is going to hit all of the columns that have an NA, all of the rows that have an NA in one or more columns. And it returns, this is a little tricky, it returns the new data frame. You need to do an assignment statement to catch that value. If you just call mydf.dropNA, it will do the computations and drop the columns and rows, but it won't store it anywhere. You have to explicitly say, do that computation and then store it somewhere by using that assignment statement, that equal sign. And then I print that out. The next thing I do is I get the interest in dropping columns with missing data, not dropping the entire row if there's a missing column, but dropping just the column itself. So that's going to chop the data frame down by one column. Axis 1 is the column axis, so we're moving along columns. The same thing applies. I have to store the result of that computation in a new variable. The next line, I print that out. Let's go back and look at the code then. I'm using that variable called cleaned. I'm using it 2 times. I'm using it when I drop NA to get rid of basically everything. And then I'm using it when I drop NA with axis equal 1. And you can see the output. I'm afraid to run this because I've been so forgetful. There it goes. The output of the first print statement when I did that drop NA is empty data frame. Pandas is saying there's nothing left. You deleted all of it. The output when I drop NA by column, only drop the columns where there's missing data. I get team, city, stadium, and opening date. I just don't have that missing column anymore. Again, remember, neither one of those is destructive relative to that mydf variable. MyDF is still the same as it ever was. Same as it ever was. But I have a new data frame called cleaned with a brand new set of data. Okay, the next thing I'm going to do in slide 13, and I'll flip back to slide 12 in a second. In slide 13, remember my DF now has NANs in the capacity column. So I'm going to go in and use fill NA to go in and put zeros where there's missing data. Sometimes it's okay to have missing data and you just want to initialize it to some known state. To get rid of the NANs, I can replace them all with zeros. Now on the previous slide, I had flashed up very quickly the concept of a threshold. And I didn't use that in my example code in slide 13, but it is worth talking about because sometimes we do this. I'm going to show you the documentation for drop NA. This is the authoritative documentation from Pandas, the people that bring you Pandas. They have, it's useful if you have some idea what you're up to. It's not useful if you're completely new because the examples frankly aren't that great. They make a lot of assumptions because they're very short. But you can get a brief definition of the keyword arguments and the positional arguments. So there's a keyword argument called thresh, T-H-R-E-S-H. And the thresh argument means that if you provide it, it will require or allow the row to survive, or the column, if you have that many or less missing values. So if a row just has one missing value, a column just has one missing value, you can put 1 in there. Now I didn't do that. I left it out and the default is 0. That means that when I do the drop NA, if there's a row or column that's missing anything, it's going to get dropped. But that's just a nice little argument to have if you want to thresh equals 1 would say, okay, don't drop rows or columns that have one or less missing data. But we replaced all the missing data. I think I just messed up here. I used fill NA with thresh. Fill NA is actually up here with drop NA, sorry. It may also be available with fill NA. Let's look that up. So this is drop NA and it has thresh. Let's look up fill NA. Fill NA threshold. Probably not. No, it doesn't. So that was a typo on my part. Yeah, there's no thresh keyword argument for fill NA. Catching up again then. Slide 13, we used fill NA to overwrite the not a number semaphores in our data and replace them with zeros. That's all good. In the next slide, 14, we are going to have a situation where we've added the same row twice. You may have gotten some data that's dirty and you've got duplicate rows. And I have that in our notebook. Let's see how our loop is going. Our loop is still running. Are we ever going to get to 100 million? That makes me very nervous, but it is what it is. So we added a duplicate row. We added Pittsburgh Steelers twice. We print it out and we see that there is a duplicate row. Notice that as with drop NA and as with some of the other things that we did, which I don't see yet right here, we have to catch this. We have to receive what's being sent back to us from the append function. So we're not changing the original data frame. We are rather creating a new data frame with the row appended to it. And I played some games here. I called append on our original data frame. I stored that new result in newdf. And then I called append again on that new data frame. It's got one new row in it, the one Steelers row. I appended another Steelers row, and then I saved that reference in newdf again. So I could do that. I can say x equal x, newdf equals newdf. I don't have to necessarily create a new variable. I just have to be sure that I'm storing somewhere what is returned by append. Then I print those out, and you can see that there's two extra rows now, and those rows are identical. All it did was add another two indices to the left side. We started at 0, index 0, now we're up to index 4. Well, I realized there's a problem, so I immediately call, as you might expect, a ready-made pandas function to drop that duplicate row. That's pretty neat. If I have any rows that are identical, they get dropped. It goes through and does the work for me. Again, one line of code. That's pretty neat. Slide 15 illustrates that. Have to catch it, receive it. The drop duplicates function sends back a result, a new data frame, and we store that reference to that new data frame in cleaned. newdf is unaffected. Okay, we still have the duplicate rows in newdf. At this point, we look at our data. It's nice because we know what it is, but if you're new to this and you just picked up this program, you might not know what is in these columns. Therefore, we add column headings: team, city, stadium, and capacity. The column headings are straightforward to add. We create a list. The list is just strings. Team, city, stadium, stadium capacity, opening date of stadium. Use the list notation in square brackets. Store that in a variable called columns. And then we know that there is a columns property of a data frame. Therefore, we just set the columns property of the data frame equal to our variable. Print it out again to verify that it worked. This is done in place. You don't have to do any assignment statement when you change the columns. So the newdf data frame is edited in place and receives a new set of column headings. We have that in our Jupyter Lab notebook. Be sure to run that. Uh-oh. I am not keeping up. There's something I didn't run. I think I caught up now. Let's find out. Okay, I caught up. Sorry about that. I kept running cells out of order and I didn't have a variable called newdf. And there it is. The two new rows. Oh, I still have the duplicates in there. Drop duplicates. Okay, now run the columns assignment again. Okay, that's better. No, the duplicates are still in there. Oh, cleaned is the one without the duplicates. Okay. So newdf will still have duplicates in it. All right, I can just continue on with my duplicates from here, I think. Yeah, I am. I'm continuing on with my duplicates. That does match the slide too, by the way. In the slide, I'm still working with newdf, and I still have two Pittsburgh Steelers rows in there, which is fine. It's not going to hurt us. It has column headings now. That's wonderful. Then I realized that duplicate row is still in there. So I call newdf, and I store the result of that duplicate drop back into newdf again. No more confusion. I don't have a new variable to keep track of. Print it out. Duplicate's gone. Column headings persist. Slide 17. Adding another row. Okay. So we're happy with our rows that we have, but another piece of data came in, and this one's a little different. It doesn't have a month and a day in the opening column. The very last column was when the stadium was opened. If it's a newer stadium, we know the exact year, month, and day because people were there and they wrote it down. If it's an older stadium like Nippert Stadium on the UC campus, which was opened in 1915, I guess they don't know what day it happened, or at least Google doesn't know. And if Google doesn't know, then nobody knows. But we can still add the column and then deal with it later. Back in the notebook, add another row that's just a little different than the others, and I'm definitely going to run this cell. Hallelujah, it didn't crash. It prints out. Look at the very last column in the data frame. All of the rows have a year, month, and day except for the last row. Okay, so we have slightly different data in that last row. In the next slide, slide 18, we're going to abandon our trend of football stadiums. We are going to add a baseball stadium. Data is the same. Team name, city, stadium name, capacity, opening date. But intrinsically, it's a slightly different kind of stadium. No problem there. Call the append method on newdf. Newdf sends back a new data frame. We can store that in the original reference newdf. So we received what was sent back from append. We just saved it in the same place. Perfectly normal to do that. Back in the notebook, let's catch us up. Did I run this slide yet? I'm nervous. I don't think I ran add yet another row, so I'll do that. And I didn't print it out in the cell, but I'm okay. I'll assume that I've only run this once. If I've run it twice, I'll have two rows with the Cincinnati Reds in them. Back to the slide, slide 19. Conceptually then, we have a problem because we don't know what kind of stadium is in each row anymore. They were all football, now they are not all football. So I'd like to add another column, and the column is going to tell the reader what kind of stadium is in that row. This is easy to do by using index notation, square brackets, not list notation this time. However, on the right side of the assignment statement, we are using list notation. This is confusing to me, is that we've got square brackets, and in one situation on the left side of the assignment, they're indexing notation. On the other situation, the right side of the assignment, they are list notation. But it does work. And with that one line of code, we've added a column to the data frame. Let me go back to Jupyter Lab and catch up. I need to run this cell. Good. I have a new column called League. It's on the far right of the data frame. It indicates what each row represents, what kind of stadium. The next thing I want to do is make it even clearer. I realize that some people don't know what NFL means. They don't know what NCAA means. So I need more clarity. And I could go in and manually edit each row and add another column and figure out what they are, or I can use what's called a map, which is really cool. The first thing I do is create the map, and the map is a dictionary. We recognize a dictionary from the curly bracket notation and the colons. We have key value pairs. This particular key value pair is keyed to what is in the league column of our data frame. In the league column, there is NFL, there is NCAA, and there is MLB. Those three things show up in the league column. What I want to do is map those three things dynamically to either football, if it's a football stadium, or baseball, if it's a baseball stadium. Therefore, I designed this map to connect the type of league with the type of sport in that league. And then I call map on the league column. Python executes map against that column using the map that I gave it. The upshot is all of the rows in the sport column are edited to be whatever they correspond to in that map. Again, with two lines of code, I added a new column and I mapped it, or logically derived it from the contents of another column. Very powerful tool. If you can build the map correctly, it's easy to use. You call the map function on the particular column and you're off to the races. Go back to Jupyter Lab again, and I need to run my map because you know I will forget. I didn't print this time. I'd really like to print at this point because I just feel better when I print things incrementally. I added a brand new cell right underneath the application of the map cell with a print in it because I didn't want to run the map twice. And it prints out, and the sport column is there, and the sport column is correct. NFL maps to football, NCAA maps to football, MLB maps to baseball. I'm in good shape. I still have a bunch of NANs though. Somehow back in my distant past, one of these previous cells, my capacities got lost. I have 4 rows or 3 rows with NAN in the stadium capacity. On slide 21, I remedy that, and here I'm demonstrating more indexing capabilities. Remember, it's row and column, so I'm using the function at on the data frame, and I can drill down to a particular row, row 0. That's that index value that's been following us all along on that row. Then I can drill to a particular column, stadium capacity, and I can slide in the correct value. I do that 3 times, one for each of the stadium capacity values that are incorrect. The problem here is that if I reorder this data frame, then this doesn't work anymore. I mean, I have to be hitting row 0, and that row 0 cannot move somewhere else. If I inserted a row, if I reordered the rows, this logic would mess up the wrong data. Just something to be careful about. I have that in my notebook. Make sure I run that to catch up with you. And I didn't print it out. I can run this cell twice. I can run the at function again, and it won't have any effect because it simply edits the same data back to the same data. The print's in there now, though. I will see that my capacities are fixed. I notice there's a typo there. That used to be 65,535. Now it's 66. But that's okay. 1,000 people will show up and they won't have any place to sit. Finally, I get really tired of having these things wrap. So I use the set option function on pandas. And this simply adjusts the way the data frame prints out. And that is slide 22. I'm also changing the index. So once I've adjusted the width of what I'd like to print, I set the index to a column name. And this happens a lot because you've derived some data and you've massaged it and you've got an index, but it came in the form of a column. But you'd like the data frame to know that that officially is your index. You can do good things with indexing. And then you just call the setIndex function to do that. That changes that integer incremental index that we've been seeing the entire presentation over to the team names. And the numeric index goes away. Catch up with you there. Back to Jupyter Lab. Run this cell, I guess. There we go. I left the print statements out, but you can uncomment those if you like to see how it prints. As a Python developer, you have to know your audience and you have to understand what will be the purpose of what you're doing. And if you're giving this notebook to a customer, an end user, and they will simply run this to look at their output, then it makes sense to adjust the print format using set option. If this application that you're developing simply outputs a CSV file or exports to a database or generates some other kind of external file, then it really doesn't matter how the data frame prints because no one's going to see it anyway. But if this thing does interact with the user, or if simply it makes you nuts that all those data frames wrap around when they print, then by all means change those numbers. Let's look over at our loop. I don't see the word busy anymore, but I also don't see the word idle, and I don't see a print here. I think my screen is just deflugeled. All right, now I'm concerned. I don't see, oh, there's busy. It scrolled off the screen. We are still busy. We are still desperately trying to count to 100 million. We haven't gotten there yet. Finally, the last thing we're going to do, well, not the last thing. One of the last things we're going to do in this presentation is rename a column, just to show that we can. And in this case, we're not going to assign our renamed column data frame to a new data frame variable. We're going to use the in place option. And that's one that is available in some function calls to data frames, particularly rename, and there are some others too. If you see in place equal true, that means that we're editing or we're affecting a change directly on that target data frame. We don't have to use an assignment statement to receive what is sent back from rename because we did it in place on our variable newdf. The problem there is you get comfortable and you forget to put in place in there, then you're debugging for an hour because you can't figure out why the changes didn't happen. So be very careful going back and forth between assigning the result of this to a new data frame and using in place, because I promise you, you will forget the in place and you will wonder why nothing happened to your data frame, and you will stare at it for hours, and then a friend will look over your shoulder and see immediately what the problem is. We rename the column. Let me go back to the lab notebook and catch up with you. So I need to run the rename. The next thing we do is add a couple more rows. I'm using a slightly different syntax here. I'm just using loc. And what I'm saying there is I'm using this as the square bracket says indexing location, indexing notation, and if the index does not exist, then it adds this row. All right, just to have a little more data to work with. Let me go back and catch up, run the cell. Now I have 3 more rows. I have a soccer team, I have a basketball team, and another basketball team. All right, I have enough data now that I can generate a useful graph. Useful being completely subjective. And I'm interested in some kind of bar graph based on capacity. How about that? So I create bins. I don't want individual stadiums graphed. I want the stadium capacities to fall into categories or bins. And then after I've got my bins, I'm going to grab all the capacities into a brand new series. That happens right here. All that does is remove one column from the data frame. Remember, we had a column called capacity, and that plops that into a new data frame, also bringing along the index too. Then I call cut, and cut consumes the data in the capacity series and allocates it into the bins. You can read about that in the documentation too. There may be some arguments here that are helpful to you down the road. But once I have the series X and the bins, which I've both created, cut will process both of those. And that's going to return back An array-like object representing the respective bin for each value of x. Okay. So semantically, it puts the categories into the bins. What do I do with that? Well, I capture that thing called categories, and I could print it out. It might be interesting to print that out and see what the categories thing looks like. I'm going to uncomment the print statement at the bottom of that cell. Then I'm going to run that cell. You can see that it tells me what category each of the capacities falls into based on the index. And then I can look at that and get a numeric feel, a tabular feel for what's happening in each bin, how many things have fallen into each bin. And I can see that 4 stadiums fell into the 100,000 bin, 2 stadiums fell into the 50,000 bin, and 3 stadiums fell into the 30,000 bin. So after I have my bins, flip down to the next cell, and I can create a histogram using the binned data. And it takes some experimentation to get the colors right and the density right, as you know. And then I apply a label to each axis. The y-axis is stadium count, how many stadiums are in that bin. And the x-axis is capacities, so you can see the upper and lower range of that bin. Finally, if you think back to when we added Nippert Stadium and we didn't have the opening month and opening day, we just had the opening year, I can do a little bit of manipulation to extract just the year from all the other columns that did have a month, a day, and a year. And the way I chose to do that was create a brand new data frame. I'm sorry, a brand new series, because I'm just extracting one column. And that series is going to be just the opening date column. And I know each of those opening dates has what looks like month, comma, day, comma, year in it. Okay? Except for the one that just has a year. There's no commas in that one. And based on that knowledge, I can do a split on the commas. If you call the split function, the default value to split on is a comma. And that's going to return a set of lists, and each of those lists are the split values from that string. That list of lists is a great candidate for list comprehension, and I'm going to ask for the very last element in the list, which I know is the year. But I only want the ones that have 3 elements in the list, month, day, and year. So when I split it, I got 3 things. And if I got 3 things, then I'm going to get the very last thing in that list, which is the year. And then list comprehension, as you know, generates a whole new list. I call that new list dates. When I print that out, you can see that I just got the year for each one of those opening days. Now notice the -1. This use of square brackets is slicing syntax. It's indexing, not list syntax, but indexing, slicing in syntax. Therefore, I'm saying give me the last element in that list, all the way at the end. It doesn't matter how long it is, I just want the last one. And I know that's going to be the year because I split it into month, day, year. But I only want the ones that have a length of 3, meaning only the ones that had month, comma, day, comma, year when they were split. Now if I take out the if, I can run this again. I'm not doing anything to the data frame that's destructive. I'm just extracting and processing. That doesn't work because some of the rows don't have that element in them. So I can't do that. That's why that if is in there. Let's Control Z that back. Now I'm only operating on elements in that list of lists that have 3 things in that sublist. And it runs now. Yay. That brings us to the end, I believe. Yes, we are at the end. I skipped over a couple of slides just in the interest of talking about the code in the notebook, but it's all reflected in the slides. I hope that was interesting. I hope that gave you a perspective into some data manipulation, and we culminated in a graph, which is always pretty cool. Thank you.